Okay, excellent. Welcome back to the undergraduate seminar. I'm super duper glad everyone's here. We've got Yuveshen Mooroogen, who's going to shine a rainbow colored light on the fundamental theorem of algebra. I'm super duper excited for this talk. Yuveshen, take it away.
All right. Thank you, Professor Glynn-Adey, for inviting me, and thank you to everyone for showing up. So my talk today is going to be about this thing called a domain coloring. So I've got the picture right there on this slide. You've probably seen a picture like this one before, maybe probably on a poster for some event. Maybe you've seen a picture that's supposed to represent the Riemann-Zeta function. And then, like me, until about a year ago, you had no idea how to read that picture. So the point of today's talk is really for me to try to demystify this domain coloring business. So I want to tell you a bit about, first off, why complex functions are difficult to draw. Then I want to tell you about how you construct pictures like these ones for functions of the complex numbers. And then finally, I'll deliver on the promise that I made in the title, which is to shine this rainbow colored light. And hopefully you see why the title applies here, on the fundamental theorem of algebra. And those pictures, well, they're pretty, which is really why I want to look at them, but they also carry a lot of useful information. So if you look at the function that I have on this slide, I can tell you that at a glance, I can figure out that this guy, if you tell me that it's a polynomial, I can tell you that it's a 4th degree polynomial. I can tell you that it has 3 distinct roots, and that all of its roots are actually represented on this picture, and that one of the roots is repeated. So hopefully by the end of the presentation, you'll be able to read off this kind of information off of domain coloring plots, for polynomials at least, just as easily. So I'll just say this again. Here's the plan for the talk. Basically, the talk is going to be split into 3 parts, and each of the parts is going to deal with one of the questions I have here. So in part 1, I'm going to tell you about why functions of the complex numbers are difficult to draw. And this is going to be very familiar stuff, I hope, for everyone, because all you really need is a little bit of linear algebra, and you need to know what the definition of the graph of a function is. The reason why I still want to go over this material is just to pin down some notation so that we're all on board and we all know what I'm talking about once I get to the later stuff. Also, just because this part is simple doesn't mean you shouldn't ask questions if you don't understand stuff. Please do, just stop me, and that's fine. Okay, the second part of the talk is really going to be the meat and potatoes, so how domain coloring works. What I want to do in this second part is work through a detailed example, just here with everyone. We're going to look at the function that takes the function f that takes z to z cubed, and we're going to see how you construct its domain coloring kind of step by step. After we've looked at this guy, I'm going to take you through a bunch of other smaller examples. So we're not going to look at them in as much detail, but hopefully they'll help you get a feel for how domain coloring works. So this is really an example-driven section. And then finally, in part 3, I'm going to go back to my title, essentially, and use domain coloring, which at this point you'll hopefully have a sense for how it works. So I'm going to use this domain coloring stuff to give you kind of a sketch of a pretty old proof of the fundamental theorem of algebra. So it's a proof from 1746, I think, and it's essentially due to D'Alembert, but the way we're going to look at it is really just through pictures. So I'm not going to do anything super rigorous or anything like that. It's kind of just a cartoon of the proof, if you want. All right, so with that being said, we can begin. What is the problem with complex functions? So to answer that, I think that it's most instructive for us to go all the way back to first year calculus and to look at a function f here that's going from the real numbers to the real numbers. By definition, the graph of this function is the collection of points x comma f of x. So it's the input comma the output. And then, of course, you know, if you want to get technical, this is the definition of the function and all of that jazz. But for me, it's just the graph. So because it's just a collection of ordered pairs, so a collection of points with two things in them, this graph is going to be a subset of two-dimensional space, so R2. And as a result, I can just draw it with a pen and paper. And then later on, you go on and you take second year calculus, and you learn about these functions, f again, let's say, which this time are going from the plane, R2, into the real line R. So again, the graph is defined the same way. It's just the input, comma, the output. The difference now is that the input is a vector with, you know, from a two-dimensional space. So it depends on these two quantities, x and y. And if I unpack it, if you want, in my definition, then I'm going to end up with a subspace, sorry, not a subspace, a subset of a vector space of 3 dimensions. So I'm sitting inside R3. So I can't draw it as easily as the previous guy, but you know, you can still come up with a reasonable picture for it, and they take some time to get used to, but you can reasonably draw them if you know where to plot them and how to turn the picture around and how to picture how it moves around in your head. But now if you go to functions that go from the complex plane to the complex plane, all hell breaks loose. So the graph, again, is just defined as the input, comma, the output. But the input and the output now have these two things that they depend on. So my input is an element of a vector space of 2 dimensions, and my output is also an element of a vector space of 2 dimensions. So my graph is going to be sitting inside this space of 4 dimensions. And well, now that's not going to be easy to draw at all. So we're going to need to do something clever to draw these functions. So that's the problem in a nutshell. Before we continue this discussion and, you know, try to solve that problem, I want to talk a little bit about notation. So for me, the complex numbers, which I'm going to write as C, is the collection of all the ordered pairs of real numbers x, comma, y, on which I define the usual operations of multiplication, of addition, and of scalar multiplication. Something you might already know is that the first 2 of these operations makes the complex numbers into a field, and the last 2 make it into a 2-dimensional real vector space. This 2-dimensional real vector space structure is the reason why I can picture it as a plane, essentially. Now, in this talk, if I have a complex number x, comma, y, I'm usually going to write it as z equals x plus iy. Hopefully everyone's familiar with this notation. And that xy business identifies a unique point on the complex plane. So, you know, every point on the plane corresponds to a complex number, and then I can represent every complex number as a unique point on the plane. In what's going to follow, it's going to be useful for me to have an additional representation for a complex number. And that's the modulus argument form, which you probably have learned about in linear algebra, likely, I think, or maybe in calculus. So the idea here is that if I take a point on the plane, then obviously I can just, you know, read off the x value or the y value, and that's your usual coordinate representation. But I could also look at its distance from the origin. So I'm going to call this quantity the modulus and write it as absolute z. And I can also look at the angle that my point makes with respect to the positive real axis, x-axis if you want. And this guy I'm going to call the argument, and I'm going to denote it argz. And then using those 2 quantities, I can just say, hey, this point is this far away from the origin, and it makes this angle. So in this way, I'm specifying this unique point. So that's the modulus argument form. It's really just polar coordinate form. So in this form, I'm writing it as absolute z, comma arc z. Oh, there's a question here. What if z equals 0? If z equals 0, then the angle doesn't really make sense, but the distance does. So I'm just going to say, I'm just going to say this is a black point and its absolute value is 0. Yeah, so I'm just going to go with that. But this is going to come up, and it's going to make more sense when I start putting colors onto the pictures. All right. So are there any questions about notation before we move on? Okay. So I promised you in the slide about functions of the complex numbers that I was going to be doing something clever to get around the problem of needing 4 dimensions. So here's something clever. I want to construct the domain coloring, so kind of in detail, for the function that takes z to z cubed. So it's a very easy function to picture, as you're going to see, which is why I picked it out. So because I have 4 dimensions of information that I want to keep track of, let me do something really cheap and consider 2 planes. So one of them for the domain and one of them for the codomain. Each of these planes contains 2 dimensions worth of information, if you want. My problem is going to be to take the information from the codomain plane and bring it to the domain plane so that I have a single picture that has all 4 dimensions worth of information. So here's how I'm going to do that. First, I'm going to take a point, let's say W, inside the codomain, and I'm going to describe it as a coordinate pair of real numbers in modulus argument form. But I'm going to write this modulus argument form in a neat way, which is using colors. So I'm going to take a shaded color wheel, meaning, it's a color wheel, so it changes color as I go around in circles, but it's shaded because I'm going from black at the origin to lighter and lighter and lighter all the way to white at infinity. So that's what makes it a shaded color wheel. So I'm going to take this shaded color wheel and I'm going to impose it on my codomain. Now, if I take my point W in the codomain, I can always write it in modulus argument form. If you look at the color wheel and stare at it long enough, then you might notice that the shade, so how dark a point is, corresponds to how far away it is from the origin. So really, it corresponds to the modulus. And you'll notice that the hue, so the actual color of the point, depends on the angle that I'm making with my chosen positive real axis. So that corresponds to the argument of the chosen number. So using the shade of W and the hue of W, I can write the polar form representation, modulus argument form representation, whatever you want, using this pair shade W, comma hue W. So that's my setup. And here's the really clever bit. I'm going to look at the set of points in the pre-image of W under F. So if you've looked at complex numbers before, you know that if I take some complex number, let's say here, its pre-image really consists of 3 points forming some triangle, unless it's 0, I guess, in which case it's just 0 in this case. But so the pre-image under Z cubed is going to be this triangle. You might have seen something like that with roots of unity, maybe. So if it was Z to the n, I would get some n gone. So all right, I'm going to look at this triangle, and for each point in the pre-image, I'm going to assign the same shade and the same hue as I had on W. So if you look at the points here, they're all the same kind of pink and the same darkness of pink as the black point that I put out on the codomain. So what's the effect of doing that? Well, if I take a point, let's say Z pink, inside the pre-image of W, then from that point, I can read its X coordinate, just from the domain. I can read its Y coordinate, also from the domain, but I can also read the shade of f of Z and the hue of f of Z, because those quantities are just going to be the shade of W and the hue of W respectively. So from that single point, from that single colored point in the domain, I can read 4 dimensions worth of information. And that's really the trick. So if you just keep doing that for every single point in the codomain and bring them back to the domain, then each point in your now colored domain is going to give you 4 dimensions worth of information. So if the picture that I have here is really just completing what I already started with the Z-cubed business. The reason why I end up with this basically 3 wedges glued next to each other is because of this triangle business. So each point in the domain is going to specify some triangle with the same color, and then I'm going to do that for every point, and then that basically squishes my color wheel into 3 wedges. But I'll say more about that in a little bit. What I want to look at this point is a few pretty basic examples. So maybe actually I'll check the chat before I go on to this, just in case there are questions. But it doesn't look like it. All right, cool. So the first example I want to consider is the case of the identity function. So by identity, I mean the map that takes Z in the domain and spits out Z. So it just takes a point to itself. So if you take some point in the codomain, you can imagine that its pre-image under that map is necessarily just that point itself. So as a result, I take a point in the codomain, it has some shade and some hue. I look at its pre-image in the domain, and I give that point, which is just, W itself, if you want, the same shade and the same hue. So if I just keep doing that to each point, then I end up copying the shaded color wheel back to my domain. So the domain coloring of the function that takes Z to Z is just the shaded color wheel. The next example I want to consider is, again, pretty simplistic. It's a constant function. So this guy is just going to take every point Z in the domain to the same point 2 minus I, let's say. Well, in this case, if I take my point 2 minus I need to start thinking about its pre-image, and its pre-image is just going to be the entire complex plane. So if my 2 minus I is some kind of purple with some darkness of purple, then my domain coloring is just going to be that color, that kind of purple, so that shade and that hue. And then if I take any other point on the codomain, then my function doesn't even go there, which means that the pre-image is going to be empty, so I don't have to color anything. All right, this is when stuff starts getting cool, in my opinion. So what I have here are the first 6 monomials, so just functions like Z to the n, where n is 1, 2, 3, 4, 5, or 6. We've already seen how you construct the domain coloring of this first guy, and that was just my identity. And we've seen in detail how you construct the domain coloring for the third guy. And if you look at the cases 2, 4, 5, and 6, you'll notice a pattern, which is that in here, I had the shaded color wheel once, so going through the colors. Over here, I have it once here, and then a second time here. In this case, I have the shaded color wheel squished 1, 2, 3 times. And here I have the shaded color wheel 1, 2, 3, and 4 times. In here 5 times, and in here 6 times. That's pretty neat. And the idea just comes down to this business of the shape that you get with the pre-image of a chosen point under each of those mappings. So in this case, it's going to be some triangle. In this case, it's going to be some square. In this case, some pentagon. In this case, some hexagon. Another cool fact with these pictures is that if you look at this guy and you go around anti-clockwise, then my colors are going from pink, orange, yellow, green, blue, purple, and then back to pink. And you'll see that it's the same here, but twice. So, you know, pink, orange, green, yellow, green, blue, purple, pink, orange, yellow, green, blue, purple, pink. And then here I'm going to go through these colors in the same order 3 times. So there really is some nice pattern to all of this. Another thing you might notice, actually Parker's pointed it out in the chat, the light area, so you know the places where I'm getting whiter, is kind of getting closer and closer to the center because those functions are essentially just getting bigger and bigger. So because they're getting bigger, their absolute values are getting larger, which means I'm getting further away from the origin, which means that in my color plot, I need to pick some lighter colors. Yeah, and then as Thomas points out, if I had a point that was just purely white, then that would be a point at infinity. So maybe you'll like the next slide, which is the reciprocals of the monomials. So what I have here are essentially poles. And if you've taken a course on complex analysis, you'll know that they're essentially the opposites of zeros. I'm not going to say more about that. Go take a course on complex analysis if you want to know. But yeah, these are essentially your first 6 in the other direction. So here, they're kind of the inverse image, right? So I'm going, instead of from black to white, I'm going from white to black. And if you go around those wheels anti-clockwise, you'll notice that I have the same colors, but showing up in the reverse order. So before I had this pink, orange, yellow, green, blue, purple, pink, but now I have pink, orange, yellow, green, blue, purple, pink if I go in a clockwise direction instead of an anti-clockwise direction. That's pretty cool. And again, it's repeated twice here. It's repeated 3 times here, 4 times here, 5 times here, and 6 times here. But yeah, that was just kind of a curiosity for anyone who knows a little bit about complex analysis. The stuff that's going to be important for the rest of this talk concerns polynomials. So let's look at these guys in detail. What I have here is a domain coloring plot for a polynomial, and actually it's the same polynomial that I had on the first slide. There are 2 facts that govern the behavior of polynomials that kind of let you make sense of those pictures. So one of them is that as you move away from the origin, the behavior of some n-degree polynomial is going to be dominated by its term of highest degree. So if I have, you know, if z to the n is my highest degree, I'll behave like z to the n away from the origin. If you look at this polynomial, what that means is that if I walk close to the edge of the picture, so this is where I'm far from the origin, then I should be behaving like its highest degree term. So let's just look at it. If I look at it, well, I'm going in like pink, orange, yellow, green, blue, purple, pink, that's once. And then again, a second time, and then again, a third time, and then finally here, a 4th time. So what that tells me is that if I look at the outer edge of the picture, I can guess that this polynomial behaves like z to the 4th power, you know, when I move away from the origin. So that lets me guess that I'm dealing with a polynomial that's a 4th degree polynomial. The other thing that might just be more striking is that there are 3 dots, 3 black dots right here in the picture. So that suggests that I have 3 roots to this polynomial. So putting those 2 observations together, so I have 3 roots and I behave like z4 away from the origin, you can guess that one of the roots has to be a repeated root. And that was a fact that I mentioned earlier in the talk. And yeah, so now you know where that comes from. But there's also another way of reading this information about the roots. So I'm going to use a different fact here, which is that if I'm close to a root with multiplicity n, a polynomial is going to behave near that point like z to the n does when it's close to the origin. So what that means is that if you zoom in around one of those black points, you'll see that around the point, if I go in an anti-clockwise direction, then I'm going through the colors in, red, pink, yellow, green, blue, purple, pink. And then if you take another 0, I'm doing the same thing. Pink, orange, yellow, green, blue, purple, pink. So these roots are both just, roots with multiplicity 1. But this guy has more interesting behavior because I'm going here as pink, orange, yellow, green, blue, purple, pink. And then again, pink, orange, yellow, green, blue, purple, pink. So that means that this guy is a root with multiplicity 2. So if I didn't know the stuff about how the polynomial behaves around the outer part of the picture, then I could just say, hey, this guy has 3 roots here, and one of them is repeated. So I could guess, again, what kind of a decomposition I'd have. So 3 distinct roots, one of them repeated. I don't know why I put this one as plus here, by the way. It could as well have been a minus. All right. So I want to give you something to play with. This is a picture of the domain coloring of some mystery polynomial. And maybe I'll give you a minute to think about it. But in the chat, can you try to give me just the form of the factorization of this polynomial? So basically, can you figure out how many roots it has? And can you figure out what the degree of the different roots are? So I guess I'll give you a minute. All right. Well, yeah, people in the chat seem to be in agreement. This is a 6th degree polynomial, and one of its roots has multiplicity 4. And then, yeah, you can guess that the one with multiplicity 4 is going to be this guy. So there's 2 ways of checking that assertion. So one of them would be to walk around the outer edge of the picture. So you'd see that we're going through the usual, the song now. Pink, orange, yellow, green, blue, purple, pink, pink, orange, yellow, green, blue, purple, pink, pink, orange, yellow, green, blue, purple, pink, and you're doing that 6 times on the edge. So I'm behaving like z to the 6 on the outside. And then there are 3 dots, and one of them is weirder than the others. So you can guess that this is the one that has degree 4. Or you could just look at the colors around each of the points. So over here, I'm going as pink, orange, green, blue, whatever, my usual song, once. Here I'm doing it once, but here I'm doing it 4 times. So this is the degree 4 guy. All right. So that's essentially how you read the plot of a domain coloring plot for a polynomial. The last thing I want to do in today's presentation is go back to my title, which is to shine this rainbow-colored light on the fundamental theorem of algebra. And so the proof that I want to talk about goes back to 1746, or at least I didn't check that it's from 1746, but there's a paper by Velleman which you should absolutely read. I'll give you the title in the end. In that paper, he claims that this is D'Alembert's proof from 1746, and that the argument that I'm going to describe below is a colorized version of this proof. So, I mean, let's just look at it. To begin, let's go back to the statement of the fundamental theorem of algebra just to make sure we're all on board. The fundamental theorem of algebra says that any non-constant single variable polynomial with complex coefficients has a root in C. Cool. In my language, that means that the domain coloring of any non-constant single variable polynomial with complex coefficients has to contain some black point somewhere. Okay, so you can sort of just verify this by inspection by just drawing some non-constant polynomials and just checking for black points. But what we'd like is to have some argument that tells me, you know, that I can certainly find one in the picture. And the crucial tool for carrying this argument out is D'Alembert's lemma. And this is super, super important for the proof. This is really the big thing that the argument I'm going to present hinges on. So it's going to be useful to internalize it. Formally, you know, in the language more familiar from analysis, let's say, what D'Alembert's lemma says is that if f is a non-constant polynomial and z is some point where the polynomial doesn't vanish, then for every epsilon, I can find a darker point within epsilon of that point that I've chosen. And I'd rather say that in plain language. So what the D'Alembert lemma says is that if z is a point in the domain coloring of a non-constant polynomial, and z is not black, then if I take a little disk around that point, then that disk has to contain a point that is strictly darker than z. And I'm going to call this strictly darker point z darker. So that's the technical lemma that I'm going to need. For hopefully self-evident reasons, I'm going to refer to this lemma as the darker neighborhood principle, just to be consistent with what Villemin does in his paper. So here's how the argument goes. Let's assume that we're working with some non-constant polynomial. I'm going to show that its domain coloring has to contain some black point. My first step is going to be to choose a very, very big square, which I'm calling here, you know, r minus r cross r, minus r comma r cross minus r comma r in the domain of f. So I'm choosing this very big square inside the complex plane. It's centered at the origin, and it's important that it's big. So all right, it looks something like that. And because this square is very, very big, I know that if I walk along the edge of that square, so if I walk along its boundary, very close to its boundary, then f will behave like its highest degree term near that boundary. So here I've drawn it as though f was some fourth degree polynomial, but doesn't have to be. Okay, so I've got this kind of behavior on the boundary. And as Parker pointed out earlier in the chat, we know that the colors near this boundary are getting lighter and lighter. So because I chose the square to be large, I have to be getting this lighter color on the outside. And that's because I'm behaving like z to the whatever highest power. So by the extreme value theorem, so just a quick reminder, the extreme value theorem tells me that if I have a continuous function on a compact set, say a closed interval, then I'm going to achieve my minimum and my maximum on that set. Essentially, in this case, it just means if you have a continuous function on a square, then you can find a smallest value and a maximum value for that function on that square. So by the extreme value theorem, which I'm going to apply to the continuous function absolute of f of z, I can find a minimum for that function inside my square. And that minimum, I'm going to call it z darkest, which makes sense, right? Because smaller points are closer to the origin, so they're darker in color. So I might as well call it the darkest point. But where should I draw this darkest point? I can't actually draw it near the boundary, which is what I did here, because f is getting lighter near the boundary, which means that if I choose a square in a smart way, so essentially if I choose my square to be large enough, I have a darker point, which is just inside where my boundary is. So there's a darker point inside, so the darkest point can't be on the outside. You know, it can't be on the boundary because there's a darker guy right there. So my darkest point has to be somewhere inside the square and not on the boundary. And that's going to be important. So because my point is sitting inside the square, let me take some neighborhood, so some disk, and I'm going to draw it centered around this darkest point. I can always do that. Now, by the darker neighborhood principle, this disk has to contain some point that is strictly darker than my darkest point, which I've drawn here in blue. So it contains some darker point, which I'm drawing here in some darker shade of blue. You know. Also, just notice I'm drawing it on the right to illustrate why I needed to be able to say that my darkest point isn't on the boundary. Because if my darkest point were on the boundary and I'm drawing a disk, then the darker neighborhood principle tells me that the disk contains a darker point, which means that my darker point could very well be sitting outside my square. And that's not going to be, that's not going to work for me in the rest of this argument. So I really needed to pull this guy inside. But now I have a darkest point and I have an even darker point sitting inside the square. But that just doesn't make sense. So I can't have a strictly darker point than the minimum, which I've already achieved. So that would be a contradiction. So my only option is that the darker neighborhood principle can't apply to my darkest point, which means that it has to be black. But this was exactly what I needed, so the proof is done. All right, so that essentially concludes the content for this talk. Before I go into the references, are there any questions about the argument I just presented? Could I summarize it? Yeah, okay. So the big idea is just follow the pictures, I guess. Pick a big square. Observe that along the big square, I'm going to behave like some polynomial, so things are getting lighter. Use the extreme value theorem to find a darkest point, and use that argument about the boundary to show that the darkest point has to properly sit inside the square. And then apply the darker neighborhood principle to show that, you know, that point has to be black because otherwise there would be a darker point sitting inside. That's the picture proof of it. Okay, cool. So there's a question, picture proof. How tricky is it to show the D'Alembert lemma with respect to? Oh, good question. Okay, I don't know. So there's probably some analytic, I mean, there has to be some analytic proof of it. I thought that you could convince yourself of the D'Alembert lemma just by looking at Taylor expansions of your function near a point, but that actually doesn't make sense because your function is a polynomial, so that just wouldn't work out. If you want a picture proof, I mean, it's really not that convincing, but you could notice that in the picture of just the usual shaded color wheel, if I draw a disk, then I obviously have to have a darker point because part of my disk is getting closer to the origin. I'd like to say that maybe you can approximate most points in this second picture, so some other polynomial, by some linear function, because then it would behave sort of like a part of the color wheel locally, which means that I could use the same argument for finding a darker point. But that has to break down at points where the derivative is 0, I think. So I don't know. I haven't looked at how you would show this using the darker neighborhood principle, like how you would show that using domain coloring. I guess that's just my best guess right now. All right. How does this relate to the fundamental theorem of algebra? This just shows the polynomial has, oh yeah, okay. So my version of the fundamental theorem of algebra was just there exists one root. I haven't said anything about the polynomial completely splitting. Like I'm just arguing for the existence of one root. So I've just conveniently left out that stuff. Anything else? If Z has pink to its left, what would it mean about the root of the color drop? Oh yeah, that's a good question. So Vincent is asking, you know, if I look at the color wheel, then it's basically oriented one way, but for the other ones, they're kind of rotated. My guess is that the highest degree term isn't actually just Z to the N, well, not necessarily just the highest degree term, but you know, the local behavior is going to be C times Z to the N. It's like there's going to be some kind of a constant there. And because that guy is a complex number, its effect is going to be to rotate and dilate the color wheel locally, which is why we get those little tilted things. I'm pretty sure that in Velleman's paper, he talks about this better than I just did right now. So if you're excited about this, go read the paper. That's kind of part of what I was hoping would come out of this talk, is that people would want to go read it.
So I see that we're headed into kind of a question period thing. And this is awesome. This was such a good talk. This is super duper good. Before we get too deep into question period, I'd like to give our speaker a break and a round of applause, because that was amazing. That was a super duper solid talk. And also, I'd like to invite people who are attending to please fill out just a quick survey about how Yuve did, so we can give him some feedback. You know, things to improve, things to change with the talk. So we're going to take a 3-minute break and then continue question period at 2:50, if that's okay with everyone.